who's going to talk about Quandela. I'll let you explain what Quandela is.
Thank you, Ruth. Thank you for the organizers to have organized this beautiful workshop and to have organized such a beautiful weather as well. So I'm Niccolo Somaschi. I'm a co-founder of Quandela, which is a newly created spin-off company from a laboratory, the C2N laboratory in Paris, in France, on the group of Pascal Senelard, which is the origin of the technology that we provide. So the idea is to provide to the community tools for the advancement of quantum technology, with the focus on providing efficient sources of quantum light. Why quantum technology? Because we have seen that light sources can take an important role in several applications of quantum technology. From quantum communication, QKD protocols, so point-to-point communication, there are several commercial products. We have also here, and they work really well. They are based on laser, but still through single photon sources they were lacking in the present years, and with some work we know, and it's been known, that still they can provide higher rates and allow higher distances for communication. And something more, they are the only object that can go beyond point-to-point communication. For example, for the realization of quantum repeaters, which are memory-based, where the information, the quantum information, is sent through flying qubits or photons to memories. It can be atoms, it can be other platform. The quantum information is stored and then is retrieved at a certain time, and these all nodes entangle also to each other. Or through measurement-based quantum repeaters, where sources are used to create complex cluster of entangled photons that can be then decomposed and sent through different nodes, and the information then is transported in different nodes at different points, so beyond QKD. But we've seen also yesterday that for the building up of universal quantum computing based on light, we have to work very hard of maximizing every component, from the circuit, from the switches, to the detectors and sources as well. And we've seen also yesterday there are many platforms, many materials that can take advantage of through single photon sources. That what we are trying to do to discuss with everyone. We are looking for partnership and collaboration in order to really put our technology and try to adapt it to the system that works already really well. So just to remind you, we have an introduction yesterday by Alex. It was explained perfectly what's an ideal emitter. So to recap, the ideal emitter of quantum light is an object that can deterministically emit pulses, train of pulses, which contain every time one and only one photon, and that has to be done at very high speed. So this doesn't exist, and what has been used up to now are approximations, so it's probabilistic sources, laser, which we all know the number of photons per pulse cannot be controlled deterministically, so in order to have an average of one photon usable for quantum communication, for example, that they have to be attenuated. So we have at the end to wait a lot of time in order to have this photon. For more complex operation, we also need nonlinear processes like SPDC, where at the end here we are always finding a compromise in between the brightness of the source and the number of multiphoton events that is created by the probabilistic nature of the process. So in order to have usable photon, we have to increase the probability to have multiphoton, but this in the long term with a high complex system, it will be detrimental and will increase the error of the system, and therefore will really push back the implementation of complex quantum computing, for example. So the idea is to use natural atom or artificial atom, because an atom is a true source of a single photon. One photon is absorbed, one photon is emitted. And our approach is to use semiconductor quantum dots, which are nanocrystals. They grow by molecular beam epitaxy, and the confinement in space allows for a confinement and a quantization of the energy level, which then means that for every photon absorbed, we have one emitted photon. And here in the spectrum, when we select one single line, that's a single photon. So the problem then is that when they're kept in the bulk, sorry for the contrast, too much sun, probably. It's very hard to collect the photon outside the bulk because of the refractive index of the material. So we have to go around this, and an approach is to include the quantum dot in a photonic cavity. So what we do is to place the emitter in between two mirrors in a micropillar structure, and by coupling the dot in the center of the pillar, then to the confined mode in between the pillar, then we have an enhancement of the spontaneous emission, so we force the emitter to emit faster. And because of the coupling of the quantum dot with the optical mode, we force the emitted photon to be coupled to the mode of the waveguide, basically, and come out from the top. So transforming an emitter which is emitting homogeneously in space in a real photonic gamma. Of course, there are many challenges. The first is the fact that this nanostructure, they grow randomly in space. So, and they are different one from each other. Second of all is we have to fight losses. And third of all, which is very important, we have to fight against all the messy environment of a solid state in order to keep the state coherent. So in the laboratory, they've been working very hard in the past 10 years, and they've been developed a technique which is an in situ lithography technique, which permits to fabricate ad hoc micropillar deterministically on each of the emitter. So what we do is to take the planar cavity as it comes out from the MBE machine, and we place it in a cryostar on piezoelectric actuators, and then we use a confocal in order to excite the system to retrieve the photoluminescence of the quantum dots, so to localize them in space and in dimension, and then use a third line, a green laser, which is exposing a photosensitive material which is placed on top, so to mark the position of the dot. So at the end, we take out the sample from the cryostat and we continue our processing. So at the end, what we obtain are single pillars which are randomly distributed, but with each one containing a single dot which is placed in the center, and each one is tailored to match the energy of the dot. So both the optical resonance is matched with the energy of the line, and the quantum dot is placed in the center to achieve maximum per cell enhancement. So since 2008, we have managed to achieve 96% coupling, to play engineeristically, reducing the losses, side losses, and bottom losses, to achieve an 80% extraction efficiency, which means that we have 80% probability to collect one photon at the outside of the micropillar for each pulse sent on the device, which give the important thing that we need, brightness. So this became, the last June, commercially available. This is the first product. It's a deterministic light source, the light, which is a single micropillar. You see bright mirrors, dot, and bright mirrors, which can operate as fast as 500 megahertz. And therefore, from this, we can retrieve at the output of a single mode fiber, not on the device, already coupled in a single mode fiber, up to 150 megahertz count per second, which is an efficiency of 35%. And the statistic, as you can see here, for the second order correlation function, where you see the photon purity, it can be 0. So we haven't studied yet how much 0 it is. We know that we need to go up to 10 to the minus 4, 10 to the minus 5 in order to be really used for QKD. And that's why we look for the experienced group here, maybe listening, in order to try to test it really on ground. That's because we know, and it's known, that true single photon source can also permit to gain a bit more from different approaches, both in the secret key generation rate and in distance. Then, if you want to do more complex operation, we need entanglement. So we need entanglement for quantum repeaters, or for distributed quantum computing, or for all the amazing thing we have seen yesterday. So what we need is photon-photon interference. We need all the emitted photon not to be only pure in terms of single photon emission, but they have to be all identical. So for this, we had also to manage to fight against the messy environment of the solid state, so dephasing, and that we have done it in the last 2 years by changing a bit the structure in this way. This is a new device. There is a micropillar in the center, and what we did is to add 4 tiny ridges which connect the pillar to a larger area where we apply an electrical contact. And this contact permits to reduce all the almost all the dephasing of the structure. So how it looks like, as you see, we have a large pad, and all around we can fabricate these pillars which are all connected, and we take a wire and we come outside. And the product now, it looks like this. It's a photonic chip, and we have it also there on the stand if you want to take a look. And this is what we provide to the community. Now here, in terms of performances, of course we have still the same operation rate, 500 megahertz. That's limited actually by detector lifetime. We can go up to 1 gigahertz itself. And the photon rate, because of the way, the regime that we drive the system, which is through resonant fluorescent, it gives 5% efficiency at the output of the fiber, which means 25 megahertz count per second of photons, which are all identical in a value which is above 90%. What we have been working lately is also to prove that these photons are coherent in a long time, because what we want to do is to create a cluster state of these photons, so many of them must be still indistinguishable among each other. What we've done, we've seen that we can still keep 90% indistinguishability up to 400 nanoseconds, which permits to use these sources as, for example, to do time encoding, where the single photon source is emitting the train of identical photons which are stored in the loop, and then through the entanglement switches, then we can entangle many of them and release a chain of this entangled photon that can be used to create, for example, complex graph state, or we can also spatially encode them, so to address the different input of an integrated circuit and to have multiple photons which still keep a high coherence. We have pushed a lot also in optimizing the optical setup. So this is an accessory which is also commercially available, which permits to efficiently collect the emitted photon and to couple it efficiently into single mode fiber. We can guarantee above 50% efficiency. What it translates is that now in the lab we play with this number. You cannot really see, we have 1.5 megahertz on the APD detector, so very low efficiency, pumping with the standard TISAF laser, 80 megahertz. This, you see the signal is very stable, but what it means that we actually have almost 5 megahertz at the output of the fiber, so we can use more efficient detector, for example, for multi-photon experiment, which means that if we use a different laser, different repetition rate, we can go up to 30 megahertz. And this is actually not the brightest source that we have in the lab that we are using. We have one of 2 megahertz, we have another one with the same value, which, just to say, it's a technology that now we master, is reproducible, we have high fabrication efficiency, and it works quite well. So as you can see here, now we perform a G2 experiment. That's a count of the 2 detectors, the 2 arms, but they be split, and it will just click, and in a few seconds we have 1,000 counts with a G2 of 1%. Same thing for HOM experiments. You can see here we have 80 megahertz repetition rate. We have counts which goes up very fast, while a couple of years ago we were waiting for 20 minutes in order to retrieve this kind of figure. And we can even post-select with a filter with 70% transmission and go even close to unity in distinguishability. So what's next is also to interface efficiently these sources with, for example, circuit. And what we have developed in the lab, we have a prototype of an active temporal to spatial demultiplexer. So the purpose here, because we emit a train of photons, we want to redirect it actively, the proper time at the input of the circuit. So we have done this for 4 photons, which means that we can achieve 4 photon coincidence, considering the emission probability of almost half a kilohertz at the output of this device. And yes, we have a design for 10 photon. We start from this, and well, the important thing is that it's linearly scalable. So we just add elements, we increase the losses, but this is a scalable device. So what I want to stress as well is the fact that we are totally aware that can be a technology which is not common for most of the community. Some people, they told me they are like afraid of cryogenics, and they think that helium now in the lab is going around and having helium everywhere, and it's very dangerous. No. So what we want to push is that the fact that we take care of also of the cryogenic side, that's with the partnership we have with AtoCube, which is this fantastic system that you don't even see. It's a cryostat, you don't even hear, because it's almost noise-free, that is full plug and play, you press a button, it's cool, and we take care of the installation, and we also train the who is going to operate the system. We stay with them, we provide also manual assistance, and we really take care of every step from the acquisition to the measurement. So that's pretty much. So where we are, so we are actually close to Paris. We are 20 kilometers far away. It's on the plateau of Saclay. It's a new technological center with several companies. The last move a couple of weeks ago is Samsung, and there we have a 2,800 square meter clean room, which is a pre-industrialization site where companies can go and install their system, and we have the support of several engineers, and that's where we work. So it's also a look ahead for the possible industrialization of the technology. And this is the founding team. Is Pascal Senelar, which is the origin of the technology, and head of the lab, Valerian Jess, myself, and since the last June we have a new PhD student, and from the few months from now we'll have Florian, who takes care of the engineering, and we are looking for more people. So if you are interested, you can discuss anytime. We are always happy to meet new people. And I want to thank as well, of course, all the people around Quandela. It's not just ourselves. We have a strong advisory board, scientific board, where you may know people like Professor Khalid Harai, Hélène Diamanti, Benoît Lebeau, and Professor Alan Spen, which I don't know yet to say anything about. And another important thing I want to thank is the entire lab of Pascal. Here we are mixed, but that's the entire team. We work together every day. This is the lab, and this is my content, and thank all of you for your attention.
Questions, please? Or nice little question, right to the back.
I was really interested by the active temporal to spatial multiplexer. Can you say a little bit more about how that works, and, for example, what type of switch technology you might be using in there?
A few years ago, I would have tell you everything, because I was a postdoc. Now, on this side, I can tell you there are standard elements, really commercial. You can find it almost everywhere. I cannot tell you really the company, but they are efficient switches. And now for the wavelength we work with, 900 nanometer, you can find really plenty. So there is no magic at all inside. Just require a bit of tricky here and there, and that's all.
See a question there, Alex.
Seeing as Graham asked my first question, I'll ask the second. What's the scope for being able to tune two sources on resonance with each other?
Thank you, Alex. I don't know if I have time, so I kept the slide here. So, we haven't focused on it, but we know it's a crucial step. It can take some time. We were focusing on finishing and concluding some experiments in the lab. So all the cryosol bays, basically they have the source running for multi-photon experiment. I'm confident you will hear more soon. But I tried to plot, imagine the question, I tried to plot yesterday what we have, and these are the three devices now running. This is one dot, this two dots from this another chip, and that's another one. As you can see, they are less than 500 picometer far away. So we haven't pushed yet in characterizing all the 30 other pillars which are in this, and the same for the other, but even with some luck, maybe we find something very close in energy. And yeah, another point would be to make them properly interfere, but let's say that with electrical contact, with the possibility to tune the dot, that's an extra degree of freedom which can help changing the wave function of each of the emitter so to properly match.
Just quickly, how much tuning do you expect? So here you say, if you've got 500 picometer spread, how much do you think you'll be able to tune each dot?
So the point is not about the quantum dot line detuning, it's about the cavity. So we have maximum efficiency when in the cavity. So the energy of the cavity is fixed. We can move around, lose a bit in Purcell enhancement. So maybe changing a bit the wave function, as I was saying. But I don't really can say a definitive value because this sample has a different quality factor than this in purpose. So the width of the cavity is larger, so this one can be tuned more than this. So it's just about playing and really doing it.
Okay, thanks.
Any more questions? One more, Johnny. Thank you so much.
Hello. So at the moment, your single photon source uses the neutral quantum dot, yeah?
Not only.
Yeah, okay. So I just wonder, so if you don't distinguish this neutral quantum dot, charged quantum dot, do you expect there is some advantage you use the charged quantum dot rather than neutral quantum dot for the generation of single photons?
Yes, there are clearly two big advantages. One is the brightness. So with the 4-level state, with the charged quantum dot, we expect higher emission efficiency than the neutral quantum dot because it's a 3-level system and the fine structure splitting limits the emission efficiency with the present cross-polarization excitation scheme. Another point is that with the charged quantum dot, we can use protocol to create linear change of cluster state. We can interfere them. We can do more interesting stuff. But on the side of the company, that means that we may need to ask the client to use different laser, not only one that you will need for neutral state, but two. One to efficiently pump the state and the other to drive the source. So it's balanced, it depends on the experience of the user, but so we use both approaches now.
Okay, there's no more questions. Let's thank Niccolo again for a very